Hello and welcome. In a previous video, we took a look at how we can evaluate a double integral of a function of two variables over some kind of general region on the xy plane. Now, we classified that region as either being y simple or x simple, and that will allow us to change the double integral into an iterated integral of the form dy dx or dx dy. And from there, we can go and basically use single variable techniques of how to evaluate the integral. But what if the region isn't exactly easy in the y or x direction? Maybe it actually is easier if we change the coordinate system. So in this video, we're going to be taking a look at double integrals where we switch the coordinate system into polar coordinates and see how that affects the calculation. Maybe that makes the region a little easier to work with, but how does it actually affect how we integrate the double integral? So let's start off with a little review of polar coordinates. First of all, we're not really going to be wanting to change the polar coordinates unless our region in R2 has maybe some kind of rotational symmetry around the origin. Now, if that's the case, let's see our conversion formulas between Cartesian coordinates and polar coordinates. For any given point on the xy plane with coordinates x, y, we can set up a right-angled triangle where x and y are the two legs of a right-angled triangle with a hypotenuse of r and an angle theta measured from the positive x in a counterclockwise direction. In this case, I'm just looking at quadrant 1 as an example. And you can see that x is the bottom leg of this triangle, x equals r times cosine theta. Y is the vertical leg of this triangle, y equals r sine theta. And by Pythagorean's identity, x squared plus y squared has to equal r squared, and a simple trigonometric function, tangent of theta, has to equal y over x. These are all the basis of being able to switch between the two coordinate systems. Now, let's see how that might affect our double integrals. Let's start off with how a double integral is evaluated over a rectangle. Now, this is a review from a previous video. Let's start off with rectangles in the xy plane. Now, a rectangle in the xy plane is essentially just an interval for x and an interval for y. Let's say that x ranges from a to b and y ranges from c to d. This rectangle could be represented as square brackets a comma b cross square brackets c comma d. And how we evaluated a double integral over this rectangle, let's call it r, is by dividing each of those intervals up into smaller subintervals. Let's divide the x interval up into m subintervals, and let's divide the y interval up into n subintervals. That gives us little subrectangles. And we evaluated the volume under a surface over this rectangle with a Riemann sum. The double integral over this rectangle r, the function f dA, is defined as the limit as m and n go to infinity of the sum from I equals 1 to m and the sum from j equals 1 to n, essentially the sum over each of the subrectangles of f evaluated at some sample point xij star, yij star in each subrectangle times delta a. And here's really the important part about the geometry involving rectangles. Delta A is nothing more than delta x times delta y, where delta x was b minus a over m, and delta y was d minus c over n. Now, the tricky part about switching coordinate systems is that geometry changes. If we're going to define a rectangle in a similar fashion, then what is the area of a polar rectangle? So let's take a look and see what a polar rectangle even means. We're going to define a polar rectangle really the same way that we define a rectangle in x and y. You can see that r and theta are just belonging to intervals. R belongs to an interval from a to b, just like our x. Theta is going to belong to an interval from alpha to beta. And I'm just really using Greek letters there to sort of distinguish the difference between a distance and an angle. But you can see how essentially the definition of a rectangle hasn't changed. But look at the geometry here. R equals a and r equal b are fixed radiuses away from the origin. They're essentially circles. And those define the edges of our rectangle. Theta equals alpha and theta equals beta, well, those are fixed angles from the positive x-axis or from our polar axis. Those are rays originating from the origin outward. And those define the other two boundaries of our polar rectangle. So you can see the shape of a polar rectangle here. We have two straight sides and two curved sides. Those curved edges are bounded by r equals a and r equals b. Now, to come up with the definition of a double integral over a polar rectangle is essentially the same. We are going to have the double integral over this polar rectangle r of a function f of r comma theta dA as being defined as the limit as m and n go to infinity of this double Riemann sum of f evaluated at some sample point r ij star theta ij star in each of these smaller subpolar rectangles times delta A. But here's the trick. What is delta A? We need to come up with a formula for the area of each of those small subpolar rectangles in terms of potentially delta theta and delta r, so that we can actually see how we turn this into an iterated integral. To come up with the formula for this area of a polar rectangle, let's start off with a sequence of simple shapes in polar coordinates. To start us off, one of the easiest shapes in polar coordinates is a circle. Let's say the area of a circle is pi r squared. And I'm going to use r2 here because now our next shape is going to have two radiuses, r1 and r2. If we want to find the area of this shaded ring with an inner radius of r1 and an outer radius of r2, well, then it's nothing really any different than just subtracting the area of two circles. Pi r2 squared minus pi r1 squared. And if you want to factor that, pi times the difference of squares, r2 squared minus r1 squared. Okay, well, let's divide the circle up into only one sector between theta equals alpha and theta equals beta, for instance. If we wanted to just look at one sector of a circle, then the area of that sector is nothing really more than just a proportion of the area of the full circle. If we were to know this angle theta, then the proportion would be theta over 2 pi radians, and we would multiply that percentage times the area of the full circle. So the area here is pi r2 squared theta over 2 pi. And you can see that those pi's cancel, and this area is r2 squared times theta all over 2. And you can see I'm using r2 here again because the last step to get the area delta A is just to remove a small part of this shaded region by using some inner radius r1. Given an inner radius r1 and an outer radius r2, the area of this shaded region is kind of a combination of these last two shapes. We need to take the area of a large circle with radius r2, subtract the area of a smaller circle with radius r1, and then multiply by some kind of proportion, theta over 2 pi radians. And that gets simplified once again. The area of this polar rectangle is r2 squared minus r1 squared, all times theta, all divided by 2. Now let's use that concept to find some kind of formula for delta A that may involve delta r's and delta thetas so that we know how to set up an iterated integral. Now that shaded area, delta A, the area of each small subpolar rectangle, has a sector angle of delta theta. And well, let's just say we have an inner radius r1 and an outer radius r2, and the difference between those two radiuses is delta r. And you can see that polar rectangle, delta theta and delta r. How do we get delta A? Well, using this formula that we just came up with here, delta A is equal to r2 squared minus r1 squared times theta. Well, that angle here is actually labeled as delta theta all over 2. Okay, well, we can see that delta A at least now has some kind of relationship with delta theta. But what about this r2 squared minus r1 squared? Well, if we recognize that that is a difference of squares, then we can go ahead and we can factor that. That gives us r2 plus r1 multiplied by r2 minus r1. And r2 minus r1 is the difference between the two radiuses, which is in fact delta r. This r2 plus r1 over 2, well, that is just the average value of the two radiuses. That is essentially a midpoint. It's actually probably one of the best places to sample inside this polar rectangle to evaluate the double integral at. So that gives us a formula for delta A. Delta A is equal to some r star value, where r star is the midpoint between r1 and r2, times delta r times delta theta. And that gives us our Riemann sum in terms of delta r's and delta thetas finally. We can see that we have the limit as m and n go to infinity. We have the double sum from I equals 1 to m and j equals 1 to n. F evaluated at some kind of point in each polar rectangle, rij star, theta ij star, multiplied by rij star again, delta r, delta theta. We are specifically forcing rij star to be halfway between the inner and outer radiuses in each of these subpolar rectangles. Now, it's because of this extra factor of rij star that when we convert from a double integral into an iterated integral in polar coordinates, that we always end up with a little extra factor of r before we have our dr d theta or d theta dr, just like we have the potential of dy dx or dx dy. But the key difference here is in polar coordinates, because of the geometry of a polar rectangle, we have this extra factor of r. Now, let's extend this concept. We know that we're not always going to be integrating over a rectangle or even a polar rectangle. But let's see how this turns into a formula for integrating over a general region, converting from x and y coordinates into polar coordinates now. All right, now here's a pretty good example of a region that looks like it's a good candidate for using polar coordinates. Say we're using the x and y axes, and we see we have some kind of region like this that seems to have kind of a circular orientation around the origin. Maybe we have some sort of outer bound that we can define as a function of theta. Maybe r is equal to g2 of theta. And maybe we have an inner function here that we can define in terms of theta. Maybe r equals g1 of theta. That way we can just integrate from theta equals alpha up to theta equals beta. Well, then we can take our double integral in our x and y coordinates over this region D, and we can turn that into an iterated integral of a function in polar coordinates. First thing we'll have to do is we'll change the function that we are integrating into polar coordinates by converting x to r cosine theta and y to r sine theta. We can't forget our extra factor of r, and it looks like this is set up to be integrated in the form of dr d theta, since we have r ranging from one function of theta to another, and theta ranging from a constant to a constant. And that's going to be our boundaries on r and our boundaries on theta. And let's put this formula into practice now by looking at how we can use polar coordinates to find volumes for some kind of a solid object that has rotational symmetry around the origin. Let's take a look at finding the volume of a tank with a conical bottom, cylindrical sides, and a hemispherical top. So everything here is very circular, all centered around the origin, or at least around the z-axis. Our cone at the bottom of this tank is going to be the function z equals root x squared plus y squared. Our cylindrical sides, well, that cylinder is x squared plus y squared equals 16. You can see that z is free, so these are perfectly vertical sides, or they are parallel to the z-axis. And our hemispherical top is given by the function z equals the root of 16 minus x squared minus y squared, all plus 20. Now, the first thing we should probably do here is realize what our top and bottom surfaces are that are going to form the boundaries of this solid region. A sketch of this region might be very helpful, but it might not be entirely necessary. Here you can see I've drawn a hemispherical top, a conical bottom, and we have some kind of cylindrical sides. Why don't we start off with the top of this region? That surface is the hemisphere. That's maybe our function f of x comma y, and that is the root of 16 minus x squared minus y squared, all plus 20. We need to convert that into polar coordinates, and what we can do is maybe a little bit of a shortcut here. Rather than replacing x with r cosine theta and y with r sine theta, we can actually see that this is nothing more than x squared plus y squared all being subtracted from 16. X squared plus y squared is equal to r squared. So in polar coordinates, we can actually see that this is the square root of 16 minus r squared, all plus 20. That doesn't necessarily look a lot simpler, but let's hope that this is going to be easy to integrate over this region on the polar plane. Now let's continue with the bottom surface. Our bottom surface is a cone. We can maybe call that a function g of x comma y. And that is the square root of x squared plus y squared. And once again, x squared plus y squared in polar coordinates is r squared. The square root of r squared could be simplified. So this function g, when we convert to polar coordinates, is really just the function r. Now we just need to take a look at the domain of integration. Looking straight down at the xy plane, we can see that this would be a circular region of integration. Our top surface is the hemisphere, our bottom surface is the cone, but we're only going to be integrating within this cylinder, x squared plus y squared equals 16. And that is a circular region on the xy plane. That is a dead giveaway as to why we should be using polar coordinates here. So our domain of integration is going to be the disk, x squared plus y squared less than or equal to 16. And once again, this just turns nicely into polar coordinates. R squared must be less than or equal to 16. Now, so long as we are integrating just once around the circle, that would be theta equals 0 all the way to theta equals 2 pi, then we don't need negative radiuses. That will end up just integrating over some of this same disk twice. We just want to have a positive radius. That would be r equals 4. And so we're going to integrate from r equals 0 to r equals 4. And that will cover the entire area of this disk, from the origin to the outer perimeter of the disk, and from 0 to 2 pi all the way around the disk. Now we should be able to evaluate this double integral and calculate the volume of this tank finally. Starting off with what we are given in Cartesian coordinates, our volume is going to be equal to the double integral over this disk D of our top function minus bottom function, f of xy minus g of xy dA. But we know that we don't really want to integrate over a disk if we can help it in Cartesian coordinates. It's way easier to turn that disk into polar coordinates, and as we've seen, even these two functions f and g also look fairly nice in polar coordinates. The boundaries for theta are constant from 0 to 2 pi, and the boundaries on r are constant from 0 to 4. That makes this really easy to try to evaluate in polar coordinates. Now the difference of functions f minus g in polar coordinates is now going to be only involving r's and thetas. We've kind of lucked out here. It's actually only involving r's. The hemisphere is the root of 16 minus r squared, all plus 20, and the cone is r. We want to make sure we have top surface minus bottom surface. Now that dA is turning into a polar rectangle version, so we have to have an extra factor of r, dr d theta. And make sure we match dr to the boundary 0, 4, and d theta to the boundaries 0 to 2 pi. Now we're extra lucky here because when all of the boundaries are constant and we can separate variables out, this will allow us to evaluate each of these iterated integrals separately and multiply the results. We can evaluate the definite integral d theta from 0 to 2 pi, and we can evaluate the definite integral of r times root 16 minus r squared plus 20 times r minus r squared. That's distributing the r across each of these terms here. We'll evaluate that integral from r equals 0 to r equals 4. Now, some of these are fairly easy terms to find the antiderivative of. 20r and minus r squared are nothing more than power rules. But this first term here, unfortunately, does require a small substitution. Now, you might be able to go ahead and evaluate that yourself. You may already understand how to do a simple substitution like that. But just in case, let's take a look over on the right-hand margin here. If we have an indefinite integral of r times 16 minus r squared to the 1/2 dr, then we'd want to make a substitution u equals 16 minus r squared. Then in differential form, the derivative of that substitution would be du equals negative 2r dr. And we can go ahead and replace dr with du over negative 2r. After substitution, we have r times u to the 1/2 times du over negative 2r. Luckily, r's are eliminated, and we have only one new variable. And this 1 over negative 2 can come out front as a constant multiple. The antiderivative then of u to the 1/2 is 2/3 u to the 3/2. And when we multiply negative 1/2 times 2/3, we get negative 1/3. So the general antiderivative is negative 1/3 times 16 minus r squared to the 3/2 plus c. Now, because this is a definite integral, we'll choose to let that c equal 0. Coming back to our volume equation, this first integral just evaluates to equal 2 pi. For our second integral, we now have the antiderivatives all ready to go. The antiderivative of that r times root 16 minus r squared we've already found by substitution. The antiderivative of 20r is 10r squared, and by the power rule, the antiderivative of negative r squared is negative 1/3 r cubed. Because this is the definite integral, we have to evaluate from r equals 0 to r equals 4. To reduce the number of fractions we're working with, it might help to pull a factor of 1/3 out of all three of those terms. That's also going to change this 10r squared into 30r squared when we divide by 1/3. Now we can evaluate at r equals 4 and at r equals 0. And after simplifying, we find that the volume ends up equaling 320 pi. Now that gives us the volume of this tank. Now keep in mind that in this particular example, we have a top surface and a bottom surface, and our domain of integration was pretty easy to find because we were forced to be within these cylindrical walls. It may be the case that we're trying to find the volume of some kind of solid that is defined as a top and bottom surface that intersect each other. In that case, if you want to find the domain of integration, you should try to find the curve of intersection of the two surfaces. Now, generally speaking, all you have to do are set the two surfaces equal to each other and then solve for that curve. That curve will be your boundary curve. And it's a very similar situation to how we found volumes of similar solid regions in Cartesian coordinates. So that gives you a little bit of a taste of what double integrals look like in polar coordinates. Once you know how to convert the functions you're integrating into r and theta, it's a matter of converting the domain of integration into r and theta. You should probably only be trying this if that region that you're integrating over looks like it's going to be easier in polar coordinates. And hopefully the functions that you're integrating are also not going to be too terrible to change to polar coordinates. Otherwise, it's not really that useful in the beginning. Just keep in mind that once you do convert to polar coordinates, don't forget that extra factor of r before you have your iterations dr d theta or potentially d theta dr. Now, this does kind of extend into our next topic, which is going to be integrating a function inside a volume. That's called a triple integral. So stay tuned. Thanks for watching, and I'll see you in the next video.